Good day, everyone. In this video, we are going to talk about logistic regression for classification. So here's the outline of the presentation. We will briefly cite some classification examples and then understand why linear regression is not appropriate for classification problems and why logistic regression is so much better for this task. And lastly, we will talk about how to train logistic regression. So first, let us quickly understand what classification is. So in machine learning, it is simply a process of categorizing a given set of data into classes. So it begins with predicting the class of given data points. And these classes may also be referred to as target or label or categories. So for example, if you receive an email, it may be classified as spam or not spam based on the contents of the email, the subject or the headers of the email. Okay? And we can also apply classification for sentiment analysis. So for example, we have a set of tweets and we can classify it as positive or negative. So some statements like I love weights and biases or great visualizations, they may be classified as positive. But tweets like I hate AI and weights and biases, so may be classified as negative. So we can also use it for computer vision tasks wherein we classify a certain image into certain categories. So in this example, we are classifying mammography images as benign or malignant. And we can also use it for sensitive to content classification. So we can detect contents that are appropriate for children to watch and those that are disturbing and should not be and should be blocked. So for instance, these images are okay and may be watched by children, but these images below have lots of blood, violence, as well as sexual innuendos, which are not appropriate for children. So we can also use it for biomedical applications, like in this example, the chest x-ray. So we can classify a certain chest x-ray as healthy or with pneumonia or with COVID-19, etc. So now, logistic regression is a method for classification. And it is also called as logit regression. And it is used to estimate the probability that a certain instance or a certain image or a certain object belongs to a particular class. So an example here is we wanted to predict a tumor as malignant or benign based on its size. So we can see here that if the tumor size is smaller, so we can classify it as benign or not malignant. And if the tumor size is bigger, then we can classify it as malignant. Okay? And we can estimate the malignancy of a certain tumor given its size. In other words, what is the probability that a certain tumor is malignant given the tumor size? So if the estimated probability is greater than 50%, then the model predicts that a certain tumor belongs to that class or labeled as 1 or yes. Otherwise, it predicts that it is benign, okay, or 0, or belongs to the negative class. So this makes it as a binary classifier or binary classification task because we are classifying a certain instance into 2 categories. Okay. Now, why can't we use linear regression for classification? So if you remember this image of training a linear regression, so essentially we have a set of predictors and a bias. And each of the predictor or features have associated weights or coefficients that we need to estimate. And we are getting the weighted na sum of the predictors and the weights. And using this weighted na sum, we can predict a certain response. And as you can see, what we wanted to have is a certain boundary that separates the malignant from the benign tumors. Okay, what it gives us is a straight line or a linear regression line. And also, suppose we add another instance, and what happens is there will be plenty of misclassifications. And as mentioned earlier, we are predicting the malignancy of a certain tumor, the probability of a certain tumor to be malignant, okay? And the probabilities are only between 0 and 1. But the linear regression produces a real value that may be greater than 1. So it is not appropriate for predicting probabilities. So unlike the logistic regression, in which similar to a linear regression model, it also computes for the weighted na sum of the input na features or the predictors, as well as the weights or the parameters theta. Okay, but instead of outputting the result directly like the linear regression model, what it does is it outputs the logistic of this result. So this logistic is noted or also called as the sigmoid na function or an S-shaped na function that outputs a number between 0 and 1. So here is the difference between the linear and logistic na function, logistic regression. So the linear produces a straight na line while logistic regression produces an S-shaped na line. So we can predict a certain response using the weighted sum of the parameter weights theta and the predictors, and it can output the result directly. We simply have to plug in x, the value of x, and we can get a certain response y. However, it produces values that are more than 1. Unlike the logistic regression, so these weighted na sum of theta or the weights and the x is wrapped into a certain na function sigmoid, so that this function sigmoid will squish in the results between 0 and 1. So because it is only between 0 and 1, it is appropriate for probabilities or estimating probabilities. And well, based on these probabilities, we can predict a certain instance as a positive or negative na label. So in this case, we can predict the tumor size as malignant or benign. Okay, so now that you know a logistic regression model is, and that it estimates probabilities and makes predictions based on those probabilities, now the question is, how is it trained? So it essentially, like linear regression, it computes for the weighted sum of the features as well as the weights, and it also computes for the probability using a sigmoid na function, and then using the estimated na probabilities, we can predict a certain response y. So suppose the probability is greater than or equal to 0.5, so we can classify a certain instance as 1, and if the probability is less than 0.5, then we can classify it as a negative na instance or 0. Okay, and of course, we have to evaluate the quality of the prediction by computing the cost. And based on this cost, because of course, as much as possible, we want to minimize the cost, because if the cost is meaning the predictions are also better. So what we can do is to compute the new weights such that the costs are minimized. And these new weights will be used to replace the old weights, or we simply have to update the weights. So this will continue. This will go on and on. We will continue updating the weights until such time that we reach the optimum na cost, okay, or until some convergence is reached. So, but the question is, what is the sigmoid na function? Or how can we compute for this? As of now, this is still unknown. And what is the cost function for logistic training? And how do we find the optimal weights such that the cost is minimized? And after finding the optimal weights, how can we update the weights? So let us answer the questions one by one. So starting